Hello everyone, I'm Kundan Panta. I'm from Penn State University and I want to present our work on the effects of gust structures on their dynamics of flapping wings. I worked with Morgan Lush and Austin Evans on this work and we were advised by Dr. Bo Cheng and Dr. Azar Panna. The structure of the presentation will be as follows. I'll be presenting three different analyses that we did in this work. Gusts are extremely prevalent in nature. For example, you can see a gust of wind blowing this tree away. But there are other forms of gusts, like this fly on the right with his flapping wings creates vortex gust structures that travel downstream and affect other flyers in its wake. To be able to achieve the level of performance that these biological flyers are at, we want to understand how gusts affects flight. The main question we wanted to answer was whether the flapping movements of wings can help in the suppression of gusts due to their greater potential for exciting the flow around them. So we set up different conditions with and without the gusts for both fixed and plunging wings to be able to answer this question. To help answer the question, we set up a gust generator in a water channel that would pitch its vanes to produce vortex gusts that travel downstream into the wing, as you can see in these videos. This is a schematic of how the wing was positioned with respect to the gust generator. The wing would plunge up and down with an amplitude of 1 inch, which is the same length as the wing chord, and the gust generator would be pitching at 3 Hz with an amplitude of 5.4 degrees and with a free velocity of 8.06 centimeter per second, which would give us a Reynolds number of 2000. The parameter that we did change was the plunging frequency. So we used the Strohal number to determine this. Since in nature Strohal numbers of 0.2 to 0.4 are commonly found, we chose a range between 0 and 0.5, which resulted in plunging frequencies between 0 and 0.8 Hz, as you can see in these videos. We used a 4-stroke transducer mounted at the base of the wing to measure the forces and torques. This transducer measures both the inertial and the fluid forces. We also had a PIV system that recorded the plunging wing as it moved and interacted with the gusts. With the PIV, we can see that sometimes the vortices generated by the gust generator hit the wing and sometimes don't, which make the interactions between the gust and the wing unpredictable. We can also notice that the frequency of the shed vortices is between 1 and 2 Hz. These plots show how the forces change over time. Over one cycle of the plunging wing at Strohal number 0.3, we can see the fixed wing on the top two plots and the plunging wings forces on the bottom two plots, and the forces without the gust are on the left side and the ones with the gust are on the right side. The main change we see between the gust and the no gust cases are that the standard deviation at each time step are noticeably higher for the fixed wing and also a little bit higher for the plunging wing. As we saw earlier, the wing-gust interactions can be inconsistent. So instead of analyzing the time series, we put all the force data at all time steps together into a single distribution and looked at the standard deviation of this instead. So this helped us see how spread out the forces and torques were at the different Strohal numbers. We can see that when we add the gust, the standard deviation increases more noticeably for the fixed wing at Strohal number 0 compared to the other plunging wings. Here too we can see that the standard deviation is higher for the plunging wings than it is for the fixed wing. However, if we look at the change in the standard deviation caused by the addition of the gust, we can see that for the plunging wings, the change is actually smaller in almost all cases than it is for the fixed wing, and in some cases the standard deviation actually is less than it is without the gust. So this could suggest that the plunging wings are better at rejecting the effect of the gust. We looked at the frequency content of the 4-stroke signals to get further insights into how the gust disturbances affect the forces. We can see that most of the disturbances are in the frequency band of 1 to 2 Hz, which seems to match what we see in this PIV image, since the vortices being shed by the gust generator are also in a similar range. If we look at the frequencies for the plunging wing at Strohal 0.3, we can see that most of the difference between the gust and the no gust case are still in the range of 1 to 2 Hz, but because of the other frequency components due to the plunging, it is a little bit harder to compare the two. To compare the frequency content at the different Strohal numbers, we looked at the average power in the frequency band of 1 to 2 Hz, since this is the range of frequencies at which the vortex gusts are primarily being shed. To remove the effect of the plunging and to focus on the effects of the gusts only, we subtracted these two powers. So we can see that for the plunging wings, the effect of the gusts in this frequency band is generally lower than it is for the fixed wing. With the exception of the force in the z direction, the Strohal number of 0.1 through 0.4 have a smaller change in the frequency content than the fixed wing Strohal number of 0 does. This may suggest that the Strohal numbers of 0.1 through 0.4 may be better at suppressing the gusts than fixed wings are. Finally, to validate if this resistance against gusts of the plunging wing helps with the predictability of the force and torques, we trained a neural network based on long short-term memory, or LSTM, to predict the force torques in the next time steps given the force torque at the current time step. And we used the errors in the prediction to determine how predictable the force torques were at the particular Strohal number. We trained a separate model for each Strohal number and for each of the gust and the no gust cases separately. And you can see some of the predictions here for the different models. So the model seems to be able to predict the force torque at the next time step fairly well. However, the prediction performance were worse for the plunging wings in general than the fixed wing, as you can see in these plots. But if we look at the difference between the gust and the no gust performance, we can see that for the Strohal numbers of 0.4 to 0.5 for almost all force components except for the torque in the y direction, the addition of the gust actually lowers the prediction error than it does for the fixed wing. So that may indicate that the predictability is maybe better at these Strohal numbers. Taking the results of the three analyses together, while Strohal numbers of 0.1 through 0.3 seem to be able to suppress the effects of gusts on the forces, only the plunging wings of Strohal number around 0.4 were able to do both the gust suppression and the force predictions better than the other fixed wings. So there could be an optimal Strohal number near 0.4, which also falls within the range of Strohal numbers commonly seen in nature. For our next step to explore the claim that there could be an optimal Strohal number at around 0.4, we will need to get more data, more force data, and train more models so we can have better confidence in our results. We also want to look at different types of gusts, such as those with different vortex shedding frequencies. We'll also want to look at the flow quantities such as turbulence intensity and circulation using our PIV system, and extend this work to other flapping wing kinematics such as pitching and yawing wings. Some of the preliminary work is being done by Morgan and Austin. I'd like to end this presentation by giving a special thank you to Roy Thompson for helping us do our experiments, and to NSF for making this work possible. Thank you so much for watching my presentation. Please reach out to me at this email address if you have any questions or comments or anything you want to point out.